and welcome to the latest of our NASA Engineering and Safety Center Guidance, Navigation, and Control webcasts. I'm Neil Dennehy, the NASA Technical Fellow for Guidance, Navigation, and Control, and I'll be moderating today's webcast. The idea to have these hour-long webcasts originated several years ago with the members of my NESE GNC Technical Discipline Team, or TDT, who thought that this would be a good way to broadly share their individual knowledge with the rest of the NASA GNC community of practice. I'm now very pleased to introduce today's speaker, Mr. Jason Everett from NASA Marshall. Jason received his BS in Aerospace Engineering from the Pennsylvania State University in May 2018. Since his start in civil service at NASA's Marshall Space Flight Center, he has been working as a full-time GNC engineer for several NASA projects, including Mars Ascent Vehicle, the Space Launch System, 2 solar sail missions, 2 lunar lander designs, and he currently serves as the mission design and navigation lead for the Solar Cruiser project and supports DevOps and GNC development for both Solar Cruiser and the Mars Ascent Vehicle. Jason's talk today is entitled Mars Ascent Vehicle GNC Targeting Routines with Considerations for Flight Software Development. As you probably already know, MAV will be the first vehicle to perform an ascent from the surface of another atmospheric planetary body outside of the Earth-Moon system, so that's pretty impressive. Jason's talk today touches on some important areas of broad interest to the GNC community of practice, I believe. We'll be hearing about how the MAV GNC team and the MAV flight software team have partnered together to improve the efficiency of the algorithm integration into the MAV flight processor. As most of you know, this is always a challenging interface to negotiate. Jason will be describing an architecture that allows both the guidance and navigation subsystems to provide code algorithms directly in C++ and the controls subsystem to provide a MATLAB Simulink auto-coded algorithms. I expect you might especially find interesting the continuous integration and continuous deployment methodologies Jason and his teammates have considered for ease of transition of algorithms codes from the GNC team into the flight software. And at this point, I would like to turn the webcast over to Jason.
Okay, yeah, great. Thank you, Neil. Thank you for the introduction.
Welcome.
So yeah, really excited to bring some of the really awesome work this team has been doing on the Mars Ascent vehicle. Kind of 2 parts of this presentation. Going to start with the targeting routine that's kind of at the core of how we're getting up into orbit. And then the second part is essentially mechanization on how we're getting this onto the flight processor. So it's some of the most brilliant engineers that I've ever had the opportunity to work with in my life are working on the MAV GNC team. And yeah, definitely really excited to share some of this content with you guys. So let me, get back into PowerPoint. Okay, so first off, I'm going to start on just essentially an overview of the Mars Sample Return campaign for those of you guys that might be not as familiar, and the Mars Ascent Vehicle profile itself before we get into GNC-specific targeting routines. So this right here is an overview of the entire MSR campaign, or the Mars Sample Return campaign. And in fact, it's already started. So you guys remember Mars 2020 launching, Perseverance landing on Mars. It's actually the objective, part of the objective of the Mars 2020 rover to go and collect some samples in these tiny little tubes that you see here. So each tube has a very small amount of Martian regolith and dirt that it's collecting, and that's essentially what we're trying to get back to. Earth. There are 2 other launches that occur currently slated for mid-2028. One of these is actually just a dedicated launch to land something on Mars called the Sample Fetch Return rover, or the Sample Fetch rover. And this rover's responsibility is purely to go collect the samples from the Mars 2020 rover and deliver it to what's called the Sample Return lander, which is on a different dedicated launch. The Sample Return lander, as you can see, is an actual lander. Inside of this lander is actually the Mars Ascent vehicle flipped on its side. And essentially what happens is that once the Fetch rover loads all of the samples onto the sample return lander. The Mars Ascent vehicle is actually thrown up into the air from what's we're calling a vector launch system. And then once it's thrown in the air, we light the candle and we continue out to orbit, which I'll be talking a lot about that specific portion of the mission. So at the same time, we actually have another launch. So lots of dedicated launches going on in this mission profile. And this other dedicated launch launches the Earth Return Orbiter, or the ERO. The ERO's responsibility is to rendezvous with the Mars Ascent vehicle in low Martian orbit. So this is after we've successfully achieved low Martian orbit. And collect the samples in this little pod that we call the Oz, or the orbiting sample. Collect all of these samples from the Mars Ascent vehicle, and then bring those samples back to Earth. So very complex mission profile for the entire campaign. Lots of different moving parts. And interestingly enough, this whole talk is only going to be focused on one tiny little corner of that, and that's the Mars Ascent system, which is essentially the Mars Ascent vehicle attached on top with the orbiting sample that we're bringing back. So yeah, lots of different interfaces with different groups for the Mars Ascent vehicle, and again, lots of fluidity with things like launch dates, with things like orbital targets as well, as we're all trying to converge on one consistent solution for the entire campaign. So yeah, that's an overview of the MSR. So now digging into the Mars Ascent vehicle specifically. This is an older version of the design, but still kind of gives you a good reference point. So this is our Mars Ascent vehicle right here. It's 2 stages. Both stages are solid propellant, so we do not have engine cutoff capability. They're both solid rocket motors. The second stage also has no avionics in the current design, so it's spin stabilized. Essentially, we've got one specific pointing direction once we're ready to ignite the second stage that we got to stick with after spin stabilization, so after a high rate spin up. Definitely on a different scale of sizes that we typically work with at Marshall. It's definitely one of the smaller Ascent systems that we've worked with. Gravity well's not that extreme. But yeah, as you can see, it's kind of a very small, almost missile-like design. So I've got a little guide to give you some guidance on just how tall this thing is. So it's a short little vehicle. Okay, and now going over just kind of a baseline ConOps of what the Mars Ascent vehicle is going to do throughout flight. As I mentioned, we start with launch. So we're on the Martian surface, and we essentially get thrown vertically, but with a little bit of an angle into the sky, at which point we ignite our engine. And that's, again, called the vector launch system being designed by JPL. After which, we've got a closed-loop guidance algorithm that's actually a derivation of the one that I'll be talking about today. For first stage, so we've got some TVC feedback from our TVC system to get us through our SRM1, at which point, eventually that motor will burn out. And then we have a long coast phase, and there's a lot of things that are happening during this coast phase. It's actually quite dynamic, and the ConOps schedule is already getting pretty packed for the coast phase itself. First objective is to steer to a safe attitude that we can jettison our payload fairing. And then after that, we start computing this algorithm that I'll be talking a lot today about, called energy management. Essentially, the energy management algorithm is responsible for finding one specific pointing orientation that the spin stabilized upper stage can achieve under, again, very tight constraints, right? So one inertial pointing direction, solid rocket motor, so you don't have the ability to cut off at all. So it's the objective of energy management to determine when the right time and what the right orientation is to burn, so we can get successfully in orbit and minimize our dispersions. But anyway, so that starts its computations up, and then after that, we are holding that one inertial attitude. We stage, so we separate first stage and second stage. We begin a very high rate spin up, so we spin up the second stage for spin stabilization, and then we ignite the second burn. And if all goes to plan, after that second stage is completely burned out, again, we don't have avionics on the second stage, so we don't have an IVU, we don't have that kind of feedback, but all things going to plan, we will successfully get into a stable low Martian orbit, meeting our orbital parameter requirements. So that's kind of the end objective here. So yeah, that's kind of an overview of the Mars Ascent vehicle profile itself. Okay, So again, the first portion of this talk is talking about an algorithm that we've been developing for a very long time now. This algorithm actually started when the GNC team was nothing more than like 2 or 3 people. Since then, we've grown quite a bit. But this concept and how to get into orbit with a 2-stage solid rocket motor configuration has been in the works for quite some time, and we've been able to make a lot of good progress on it. So this is kind of an overall view of what the algorithm does and kind of how it operates. So fair warning, lots of math equations coming up in this first part, but we have some visualizations too. So all right, so this is an overview of the algorithm itself. So this is assuming that we've successfully completed first stage. And if you guys are interested in the guidance running on first stage, it's a derivation of what I'm about to show. I'd be happy to talk about that a little bit more offline. But let's assume, right, that we get into a ballistic trajectory and we are on our way coasting up to apoapsis after a successful first stage burnout. What we can do is we can take any generic point, any arbitrary point on this ballistic arc, assuming you're above the surface, and that any arbitrary point will have some position and velocity. That's known to us. That's IMU data. What's interesting is that this is a 2-dimensional case. It's a little bit more complex in 3D, but you can assume that at any point along your ballistic arc, if you want to target a specific semi-major axis, there's actually a closed form impulsive solution that allows you to do that. So what that means is that depending on where this arbitrary point is along the ballistic coast, you do have a solution that will get you to some semi-major axis value. And that's our leading orbital requirement right now, semi-major axis. The difference in between the desired velocity and your current velocity is what we're calling velocity to go. You can think of velocity to go as essentially this pointing requirement first off, because it does give us a direction to point. It's essentially the direction that we want to throw our impulse in. All right, so again, this is for just one arbitrary point along this ballistic arc, right? What if we run this type of equation right through all arbitrary points on this ballistic arc? Well, when you do that, we start to see this really interesting behavior where, and it makes sense when you think about it, but what you see is that near apoapsis, it actually the magnitude of velocity to go, so the cost of the maneuver is near its minimum. Not exactly at apoapsis because of finite burn considerations and plane changes, which I'll be talking about. But it's very close to apoapsis. So what you have is essentially almost a parabolic shape built up with your velocity to go. And what we can do is we can design and size the 2 stages of our vehicle such that at some point the velocity to go magnitude is equal to the delta V on board the second stage. At which point that essentially gives us authority to light the candle, so to speak. And because of the fact that the velocity cost is equal to the estimated velocity that we have on board, then we can kind of guarantee that, hey, we're going to hit a good orbit if we just like hold fast in this orientation. So yeah, and you can see it's very parabolic in nature. It's a very stable type solution space. And it occurs twice, once before apoapsis and once after apoapsis. So yeah, that is an overview of what energy management does. It's matching up of energies, which allows us to essentially say, whatever we've got on board, that's exactly the right amount of energy we need to get into our constant semi-major axis target orbit. So I've got a visualization of this to kind of show what this looks like over the course of a ballistic arc. This is obviously very exaggerated. This is certainly not the ballistic arc that we're going to be trying to hit with first stage on MAV. But as you can see, this faint green orbit here, right, is actually a constant semi-major axis orbit. So this axis right here will not change in length over the course of this ballistic arc. And essentially, that represents the instantaneous target solution. And as you can see, if we're assuming that we've got a certain amount of estimated delta V on board, there is a certain time during this coast where the delta V on board will equal the cost of the maneuver. And again, as you can see, there are 2 points where this occurs, one before apoapsis and one after apoapsis. Right now, part of the MAV ConOps is to essentially ensure that we're burning at the first opportunity to do so. We don't have spots in the code yet to handle, a new opportunity that might arise later, but it's certainly something that we're going to implement. And it's cool because we kind of have two unique opportunities. We have 2 unique opportunities to kind of hit the orbit that we want to hit. So yeah, this is what we call a well-behaved ascent. It's a well-behaved ballistic arc. Sorry, when you have these 2 solutions, so you want a little bit extra energy, if that makes sense, to handle things like dispersed cases and unknown environmental factors that might, again, instead of having it right here, you might have kind of a wider range of where that parabola, so to speak, crosses that 0 line. So you do want a little bit extra energy. You obviously don't want too much because then you're just being inefficient in your system design. But let's say you do have a case where something is not well behaved. You can think of this example I'm showing as essentially a first stage insertion orbit that just didn't get us there all the way. Maybe it was super windy or dusty that day, or or something happened with our SRM-1 propellant, and we just couldn't get enough energy, and we couldn't get a high enough arc that we actually expected to get. In this case, what the algorithm is designed to do is essentially still burn at the most optimal location. You don't necessarily want to just assume mission failure. And in fact, actually, in some dispersed cases, we do have this kind of delta in the super low energy dispersion cases, where essentially the delta V cost of the maneuver throughout the entirety of your ballistic profile is never going to achieve the actual delta V that you expect to have on board. But again, that's actually kind of the tail end of our dispersions, so to speak. It doesn't mean you don't hit successful orbit. You're certainly not going to hit it with enough, the same amount of accuracy as the delta V is actually aligning. But it is important for our algorithm to also consider these low energy cases and make sure that we actually have something that we can do in that scenario. So yeah, those are 2 examples. One being a well-behaved orbit, and then this one being not so well-behaved. But energy management throughout the years, we've found a solution essentially that can accommodate both of these. So, all right. So energy management. This is where some of the math starts coming into play. There's 2 components to it. There's an inner loop and there's an outer loop. You can imagine the inner loop being, what is my delta V at any given point? You can imagine the outer loop being, okay, what is the right time throughout this ballistic arc where my delta V's equal each other? So essentially the outer loop will use the inner loop to compute the delta V, but then the outer loop is responsible for determining where along that ballistic arc the delta V's are going to match up. And I've got a mathematical description of both the inner loop and outer loop that I'm going to be talking about. Let's start with the simple case. This is assuming impulsive. Now, since then, this is actually what we started with in our design. Since then, since this time, we've been able to make a lot of good improvements to the fidelity of the algorithm, such as handling finite burns, and so on, and such as handling inertial pointing directions, kind of built into the equation, which I'll show on the right-hand side in just a couple minutes. But so let's say that you are at any arbitrary point along the coast. This is essentially the same algorithm the same diagram I was showing before, but with the math equations behind it. First thing we do is we define what's called a target frame, or a guidance target frame, which essentially represents your radial downrange and the anti-parallel to your orbit normal. For those of you guys that are familiar with PEG and the heritage PEG, and now for SLS, PEG's derivation, they actually use a very similar guidance target frame representation. It's a good way to kind of organize your equations in a frame that makes sense with no requirement to be inertially fixed. So yeah, it's really simple at this point. We've got a position magnitude. With a position magnitude and a desired semi-major axis, as you can see, it's quite literally just vis viva. That's how simple it is to come up with a desired velocity magnitude. The other component of this is that your I hat z is essentially the downrange direction in your target orbit. So not in the orbit you're in, but in your target orbit. That's what allows for 3-dimensional plane change. So at this point, we're using vis viva to come up with the desired velocity. We have a current velocity, and it's that easy. You can compute velocity to go. So for a while, this was the algorithm that we were flying. It was a very simple, impulsive. It was a very simple, impulsive derivation that allowed us to, again, compute VGO at some arbitrary point in our ballistic coast. But since then, we're always striving for improvement, and there are some improvements to be made with this model, such as handling finite burns, and such as assuming that you are inertially fixed. So we ended up expanding this mainly to handle this finite burn type situation that we were running into. But same starting conditions, right? You've got some position in the coast that you're taking a look at. We are approximating gravity over the entirety of the coast with just your starting position. The reason we're allowed to do this is because of the fact that our position vector doesn't really change much over the course of the burn. We could even make that more accurate with our burn arc prediction, and I'll show that in a second. But the next thing we do is we take one iteration of our velocity to go, which you can either use the iteration from your impulsive decision, or you can just start as priming velocity to go with the zero vector. Either way, the algorithm has been proven sufficient throughout the entirety of MAV's operating environment, where whatever you want to initialize velocity to go to, you'd be fine. But using velocity to go and using some pretty simple linear dynamics, you can actually come up with an estimated final position and velocity after you perform this maneuver. There are, for some guidance geeks out there, some assumptions that go into this. I'll leave it up to the reader. I've got some papers that I reference later that go into the derivation a little bit further. But yeah, so we have an estimated final position and velocity afterwards. Now that final position and velocity is then what we use to define our new target frame. So now we have a target frame at that final position. We also know at that final position that we have, once again, a desired velocity that we'd like to achieve, which is once again computed by a simple vis viva. At that point, we know that we have a desired velocity where we want to be, an estimated velocity of where we're going to be at the end of the burn, and we can take a delta from those two components and essentially update our velocity to go on the next iteration to get more accurate. And it's pretty awesome how quickly this actually converges. We've seen that only priming, but running an iteration with essentially 2 iterations per minor cycle is plenty sufficient to narrow in on a stable velocity to go. And I've got some results that show the mechanization of that later on. But yeah, so that is how we've expanded this simpler model into a more complex model that can handle things like finite burns. And again, very similar, for those of you guys that have read through PEG and even the iterative guidance mode, what the Saturn V flew with, very simple, very similar assumptions are going into this model when it comes to computing finite burn and, delta V miss and all these parameters and how to set them up. Okay, now again, this is all for one point. So we now know how to compute something at one specific point in the orbit, but that's not really enough for us because we need a cost-effective way. And when I say cost, I mean computational. We need a cost-effective way to do this throughout the entirety of the orbit and narrow in on a solution where our velocity to go is going to be equal to the delta V on board the vehicle. So how do we do this? Well, that's what the outer loop is for. So I'm going to go through essentially now what the outer loop does. And whenever you see a VGO value, you can assume that the inner loop is running to compute that VGO value. All right, so we start by an assumption that through inspection, it's clear that velocity to go over time or true anomaly, we actually switched to true anomaly for some computational reasons that I can maybe talk about later. But yeah, we found through empirical inspection that it takes the form very closely of a parabola. It's not exactly a parabola, but it's very close to a second order polynomial. As you can see in this example, this does not look like a polynomial, but it's a very vast over exaggeration just for the sake of the example. But yeah, we were taking a look at this kind of form. We're like, hey, definitely it's very, very ripe for a polynomial type fit. And the polynomial that we're using then would look like this. The velocity to go at any true anomaly is based on the true anomaly plus a set of coefficients. So the objective then first is to find out, kind of what these coefficients are. And then when you have that polynomial defined, find a true anomaly where the velocity to go equals. And it's all analytical and it works out works out pretty smoothly. So that's what I'm going to kind of show here. So this is the new iteration scheme then. To start, we prime with any three true anomaly values. We found that as long as your true anomaly values to start encompass the majority of Ascent, that it actually converges fairly smoothly. And yeah, we haven't seen a lot of issues where we have like rapid runaway or divergence or anything in our true anomalies. It's partly because the velocity to go is so close to a parabola itself that it's a pretty good assumption. But anyway, yeah, we have three different true anomaly values. And at those three true anomaly values, we then compute three velocity to goes using our inner loop. So now we've got three true anomalies and three velocity to goes. Once we have those three, we can construct a polynomial. And the equivalent of constructing a polynomial really means you're just solving for the coefficients. So now we have these coefficients solved for this equation up here. Once we've solved for them, then we can find at what point on that polynomial, and this is purely the quadratic equation, but yeah, we can find the point on that polynomial where our velocity is equal to v cap, which is the capability of the second stage. So what amount of delta v we expect to see on the second stage. So at that point, we now have a new estimate of where our true anomaly should be for when we burn. We move to that true anomaly, and we once again, so we shift around we shift our new true anomalies for the next iteration around the burn location, and we get ready for the next iteration. And that's what the outer loop does. So it's the seeker method that kind of goes into the proper basin location for when these two velocities are equal to each other. We found that just running the outer loop just once at 1 hertz. So priming it, and then every 1 second we update the true anomaly bounds. We found that to be more than sufficient for very, very tight convergence. So again, we're lucky in the sense that we have a very well-behaved equation for velocity to go over time. So it's very easy for the optimizer to converge very quickly. This is an important parameter here. Essentially what this is you're recomputing the true velocity to go, and you're comparing it to the polynomial velocity to go. This is an error term that essentially will go to 0 the more that you iterate. But it's a good kind of performance metric for us to track throughout flight to see how close we are to the actual solution. The way you do that is once you have a true anomaly, you essentially recompute the true velocity to go. At that point, you compare it to the velocity value of the polynomial. So that term right there will go to 0, as you can imagine, once we get closer and closer onto a solution. So yeah, that's the outer loop. All right, I'm gonna breeze through this here, but I do have a full listing here, just in case you guys are interested. This is in a paper reference that I have later on, but this is the energy management algorithm. So this is the inner loop and the outer loop. We've got a lot of constants, right? Your target orbital plane, target semi-major axis. You also have initial values for your true anomaly bounds. You have incoming position of velocity data. If it's the first pass, you perform this computation for, again, if you guys don't remember, this is part of the target orbital plane. So essentially, this set of this vector that's created, this unit vector, will provide you with the anti-parallel. And this is the exact same derivation as PEG, by the way, for target orbital plane. Set a bunch of values to the 0 vector. Again, I mentioned you could use the impulsive computation to kind of prime your velocity to go. We found that just setting it to 0 is easier in an algorithmic sense, in a mechanization where we actually code it. And it's plenty sufficient for convergence. Okay, and this is the outer loop. So we run this once every 1 hertz. We compute our perifocal frame, which makes things way easier than actually using like a 2-body propagation or something. If you have your perifocal frame, if you feed a true anomaly in, you can instantaneously get position and velocity at a later time, which is like super computationally efficient and very helpful for us. At that point, we have 3 true anomaly values. You see F0, F1, F2. We have 3 velocity to goes that you get out of this F. This F is our inner loop. Once we do that, we can actually construct a system of equations that you see right here that uses the true anomalies and the velocity to go magnitudes to get you your coefficients. Once that's done, if you guys remember from, I think it was algebra 2 in high school, but the quadratic equation, whenever we learned that, Negative b over 2a, if you guys remember, it can be used to find the minimum of that polynomial. Then, once you know that the polynomial is in range, you can also compute the quadratic equation. No need for roots or anything on board. We have negative square root checking and everything like that, part of our flight software. But yeah, it's a very simple quadratic equation to find the true anomaly location. And the min here, again, is for the first true anomaly because there's two places where it'll occur, the minimum location. And that's it. Once you're at that minimum location, feed it back into the inner loop, compute the true VGO, get your delta V error, that little error, which will go to zero at the more you run this. But that's it. So that's the outer loop. Every time you see F here, I'm going to skip over this because this was in the other slide, but every time you see F here, it means run the inner loop. And then the next iteration, essentially, you're adjusting your polynomial bounds to be around your burn polynomial. And that's it. You set your updated VGOs and you can just chill for an entire second on the flight processor and get ready for the next iteration. So yeah, that is kind of the full listing of where the energy management algorithm stands today. Yeah. So again, this is referenced in a couple papers and everything. So no need to spend too much time on it, but I did want to throw that out there. All right, talking a little bit about performance, what happens when we actually fly this thing. We've got a few performance metrics that we take a look at. One, we call it DTIG, or the delta time of ignition. What this parameter represents is how much earlier than apoapsis we actually want to ignite. You can imagine if you want to ignite really, really early, really way before apoapsis, that means your vehicle has a lot of excess energy. Whereas if your delta TIG is 0, that means you're burning right at the most optimal point and you might not have enough energy to actually complete the maneuver. So very important metric that we track. The second metric that we track is one that I already talked about, the delta V error. How close is our polynomial solution to the actual solution at that point? So another important metric that we want to track. This was from a simulation run that we ran with our 6DOF toolkit that I'll be talking a little bit about later when I talk about flight software, interactions. But as you can see, there's these distinct steps in the solution for delta TIG. So essentially, this would, as an example, burn 70 seconds before apoapsis versus burn 50 seconds before apoapsis, right? That means, well, we're having to burn closer to apoapsis, which means our orbit's losing energy a little bit. In this specific example, these were actually RCS thrusting events, which is really cool to see. That means that this algorithm is able to detect small enough orbital perturbations, and it's almost an instantaneous feedback in the algorithm to show basically an updated location along your thrust arc that you need to be burning. And then in this case, you also see a small uptick in the delta V error. So it's the delta in between your polynomial and what it actually is at that point. But as you can see, the algorithm has no problem. It only takes, 1 or 2 iterations, in this case, 1 or 2 seconds, to converge back onto a solution. And again, what's really cool about this polynomial scheme, it's very low computational power. So that one hurts. If we wanted to bring the time of these spikes down, we could. Also notice the scale. it's a very small uptick that we experience, and even burning with this high of a delta V error would still be completely sufficient for us. Okay, so as I mentioned, we're running this at 1 Hertz cycles. For the inner loop, I mentioned that you can run the inner loop multiple times to kind of converge onto a VGO solution that's a little bit more stable. We are running this twice. What we found is that only running the inner loop twice per outer loop is plenty sufficient to essentially kind of hit this minimum bound. And after this minimum bound, there's still other errors. There's no drag in this equation. There's no J2 perturbation of our oblate spheroid that we're flying from. So there's other considerations, but to get only two primers, or only 1 priming technically, but 2 iterations is all that you need to kind of hit this low point. And then after that, you start to see diminishing returns from running the inner loop multiple times. So through this kind of error analysis with delta V error, we can find what the most computationally efficient amount of iterations is to run, where we can still get the accuracy, but we're not overrunning our iterations, so to speak. So yeah, So that is energy management, which again is only one small component of all of the GNC system. We've got a lot of really awesome parts of our GNC our GNC architecture. But after we have all the math down and the math looks good and we can fly it in a simulation, we also need to consider how to mechanize it properly and how to get it on a flight processor and how to make sure that we're not running into errors, and how to make sure that we can do this within the right amount of computational power, processing power on board. So the second part of this presentation is going to talk a little bit about considerations for flight software. So what we need to consider and what our current design methodology is for getting this on board the vehicle in the smartest way that we can, essentially. And to start, it's important just to see what our relationship is to flight software on the avionics board. So the flight software team, again, an awesome, really a brilliant group of individuals at Marshall as well, running the flight software team for the Mars Ascent vehicle. They are running the core flight systems architecture. So that was the architecture that they had decided after a trade study that they had ran about a year ago. Going into the flight software architecture, the actual board itself, we have like raw data. We've got some ground uplinks coming up through the transponder. Essentially, we've got a lot of different incoming data sources that are being pumped into the avionics and the flight processor itself. CFS, the way CFS runs is essentially a set of a bunch of different apps. So you might have an app that's responsible for just storing long-term data. You might have an app for processing raw sensor data coming in from the IMU. You might have an app that's responsible for TVC actuation, so on and so forth. So lots of different apps that are running on top of this kind of core CFS, CFS base. The app that we care about, as you can imagine, is the app that runs GNC. Kind of a misnomer, but the app is called the Nav app. The Nav app is responsible for running all of GNC code. So going into the Nav app itself, we have some data tables that have like hardcore, hard-coded configuration parameters. And we also have some sensor data coming in from our IMU. And then within the Nav app itself, I only just presented a very small subset of what the entirety of the GNC system is responsible for handling. We've got navigation, guidance, and controls. Navigation is responsible for sensor filtering, for position, velocity, and attitude propagation and estimation, for performing some gyrocompassing activities that we actually need to be running well before we even launch. So lots of very important related activities going on in the navigation subsystem. The guidance subsystem is just another component of the entire GNC architecture. And this one, the guidance is responsible for example, computing orbital elements to be used in our algorithms. Energy management, again, is one of the algorithms that we're running in the guidance subsystem. We have steering filters to make sure we're not throwing huge step functions to controls TVC. We've got a mass estimator. We have a mission manager to determine what is enabled and what is disabled and what's our attitude at a specific phase of flight. And then we're also responsible for reporting out separation and ignition commands. Okay, and lastly, the control subsystem. We have a PID running for GNC. We have RCS. We've got a phase plane controller running for our RCS, or reaction control system. And then we also have some command validity checks, making sure that we're not turning on too many RCSs at the same time. Making sure that we have the RCS not pulsing too quickly to design specifications. So just some generic validity checks as well. So lots of really cool computations that weren't even in this presentation going to the GNC. After that, we have TVC, RCS, and separation commands all going to their different apps in the core flight system architecture. And what comes out of that then is the actual vehicle actuation. So the vehicle modifying what it's doing after these different apps are modifying their things internally. So that's how we relate to flight software. Essentially, we exist in what's called the Nav app, and we're responsible for designing the software and providing the code specifically to go inside of this Nav app. Okay. Now, when it comes to actual development of the GNC, code and algorithms and everything, we're doing something kind of interesting on MAV. So we've got two simulations that we're running right now. We have our Mantis toolkit, which stands for MAV Analysis Toolkit in Simulink, which is our MATLAB Simulink model. And then we have Maverick, which is our flight heritage C++ 6DOF tool. So we've got a MATLAB 6DOF and we have a C++ 6DOF. Inside of Mantis, we then have a Mantis-specific plant. We've got Mantis-specific sensor models, and we have a GNC, a MATLAB implementation of our GNC. So this is coded and designed and developed in MATLAB language. Then in Maverick, we have, again, Maverick-based C++ plant model, a Maverick-based C++ set of sensor models, and then we also have a C++ implementation of our GNC code. So two different languages are actually being used to create our GNC code. And then what we do is, you see the title, Development Matrix. We do this kind of crossover thing. And this crossover thing looks like this. We can autocode our MATLAB GNC, and we can throw that into the same interface that the C++ GNC is being used for in Maverick. This essentially allows us to plug and play either GNC model and compare the differences. Inversely, we also have the ability to create a MATLAB MEX, which is basically a functional interface where you can throw C++ code into MATLAB as a function. So we can MEX in our C++ GNC code, and we can run that in Mantis. So what you get is essentially this crossover of our different GNC implementations across two different simulations. You can look at this as kind of a two-dimensional matrix, which is why we call it a development matrix, essentially. Where on one axis, you have what 6DOF simulation you're running, either Mantis or Maverick, and then what GNC model you're running, so either C++ or MATLAB. Starting with just the MATLAB sim and the MATLAB GNC. What this does is this is essentially the layout that our team uses for all of our main deliverables. So this is what the team is most comfortable in developing in, and it's what we use for whenever we have products that need to go out to the broader distribution or the broader project or program. This is also where we're doing the majority of our GNC development. So this is where everyone on the GNC team does all the development. And then lastly, we kind of use this as a feature test bed. So if you're trying new features or everything, this is where you'd probably do a lot of the work. We then have on the other side of the matrix here, Maverick, so C++ simulation and C++ 6DOF, C++ GNC. In this case, we essentially use this for verifying our simulation in MATLAB with a heritage simulation. Maverick has been used for SLS and for previous missions as well. So there's a lot of flight heritage in the Maverick simulation. We also are using this to kind of practice our translation. The whole objective is that the GNC itself is not the code. The GNC is a set of abstract algorithms that we need to learn how to translate into different components. So that's kind of what we're using that for. When it comes to running our C++ GNC in Mantis, great for our group to learn MATLAB mexing capabilities. It essentially allows us to, whenever we have C++ code now, basically build it right into MATLAB. A few folks from MathWorks have been essentially very helpful in getting us up and running with the MEX framework. We've actually been able to utilize this for other programs already, this mexing capability of C++ code into MATLAB. This also is used, again, just for C++ model verification from the Maverick sim. And then lastly, on the other side, let's say we want to run Maverick, but we use our MATLAB GNC. Well, this gives our team a good opportunity to test our autocoding capabilities. So what this allows us to do is essentially we have our GNC code converting back into C++, trying to get the interface into Maverick. What this does, it kind of allows us to verify our autocode as well, where we're testing the pseudo MATLAB, but no longer MATLAB, into the other simulation. So it's kind of a development matrix where you can develop anywhere in this square. You can develop code anywhere in the square that you want. But we have kind of a primary that people like to deliver in, and we can use all of this kind of for cross verification of our tools. So yeah, lots of benefits come out of this multi-language model. Interestingly enough, there was a big study a while back to go either one way or the other, which we still will do eventually. That's still in the trade space. But it's been really interesting so far to kind of maintain both models, because we get this, we essentially start building up these definitions of what an algorithm is rather than what it looks like in code. And it really helps you kind of understand the different sub-level components of your algorithms. So this is an example of the guidance subsystem in both our MATLAB code and our C++ code. As you can see, over time, we start building up very similar submodules. The submodules have very similar different routines across the languages. So it's breaking down, that again, it's that translation component that's like so super essential for actually understanding the concepts themselves. And this is kind of a design iteration that I'm about to show you right here. So we start with just development, right? MATLAB and C++ GNC. We've got people working on both. We compare them to one another with the auto-coded version of the MATLAB GNC. And then we have an update step. And this update step is essentially where we learn from both C++ models and we incorporate knowledge across the two. So in one case, we use the C++ GNC, which is obviously we're writing it ourselves so we can define kind of the architecture of the code. And we can essentially update our MATLAB GNC code to produce a more readable C++ autocode. So in one way, our knowledge that we learned from C++ GNC is getting updated to MATLAB. Inversely, and again, that cross iteration is, if there are structure or architecture recommendations that come out from autocode, and if we're like, hey, we actually really like that design, then those design methodologies can go the other way as well, where we learn from the autocode and then we incorporate it into the standalone. With the idea of after enough iterations, and we are getting amazingly close to this, where our autocode and our hand code actually just line up with one another. So it's been really cool to see this process. And then deliveries. So deliveries on the next slide. How do we take this kind of iterative design process and actually pass it off to flight software? Okay, so this is the same plot that you had seen before. First thing we do is we go through continuous integration. Continuous integration, the whole concept is essentially run a lot of like automated procedures for us ahead of time that essentially allow us to do things like unit testing, static analysis, even requirements verification as well can be used in continuous integration. So yeah, we've actually implemented continuous integration pipelines now into 3 different CI/CD suites. We're currently using Bamboo, but in the past we've also implemented into GitLab. We also have a custom Jenkins instance on our Linux servers. So lots of options available in our group for CI/CD testing. And once that's done, once we've successfully passed all of our requirements, what we do is we pass off the code to the flight software team with an API, essentially with a user's guide on how to actually use the modules and the functions available in our GNC library. What the flight software team then does is incorporates it into the CFS Nav app using the guidance of our API and the now CI/CD verified code, and they work it into their application, their Nav app. Another cool thing that our continuous integration does is creates automatic documentation generation for us. So as you can see, this is an example of a Doxygen output. We actually have a website for NASA internal folks to go to, where if they wanted to just, implement mapGNC or look at a function or something, they can just go to that website. And it's available to anyone that has access to the NASA server. They can scroll through the documentation and everything, and they don't have to worry about, which documentation version do I have stored on my local machine. You can just go right to the website. You're guaranteed to have the same documentation version that got pushed through the CI/CD pipeline. So everything is, version controlled and everything for you, so you don't have to worry about, what version you have. Okay. This is kind of a future work slide, so to speak, but this is essentially the idea that we've been working on taking this abstraction layer one step further. So going back to our 2 6DOF simulations that we're using in this kind of development matrix, we've got plant models and sensor models that are totally separate. And then we have a box where you can imagine where the GNC code will go. Something that our team is considering, and we haven't done a lot of work on this yet, but we're really excited to start messing around with it, is essentially instead of developing the API and then having someone, build in that API into elsewhere, essentially allow both simulations to run the CFS app itself. So take the entirety of the CFS app, all of the awesome work that flight software is doing on actually developing the app infrastructure, combine that with the API, and be able to just run that on, on both MATLAB and Maverick. Now, this would require, a CFS emulation interface. This is not the first time folks in, not necessarily our group, but folks on Mav have done this, where we emulate a CFS app, by the way. But yeah, so the whole concept is to take a, develop an emulation interface for both MATLAB and for C++. That way we can just develop the entire CFS app itself in like one consistent location. And then you don't have to worry about developing another, API interface. And then you have one consistent app that you can essentially pass around. And with that one consistent app, we can then pass that app through CI/CD pipelines to run unit tests for GNC. And then after that, it's direct delivery into flight software. So that nav app itself can then just kind of be plug and play directly into flight software architecture. No need to develop another API on all of our, or no need to develop another, another interface for the GNC code. Okay, that was definitely a mouthful. Got a lot of stuff going on, but as a quick conclusion to those two separate parts, I can't stress enough how awesome it is to be a part of the MAV GNC team. There's some of the brightest individuals that I've ever had a chance to work with are really doing amazing work every day on the MAV GNC team. And there's some design principles that we like to kind of unofficially follow. How do we develop and implement our GNC code faster? Are there design methodologies or anything like that where we can take something from ideation to concept development to complete implementation? How can we go through that process easier? Are there design guidelines that we can follow? Are there abstraction models that we can follow? So on and so forth. Another one, how do we automate redundant tasks? So whenever we have a workflow that seems to be very repetitive and seems to be wasting time, it's almost kind of an instant red flag for the MAV GNC team to look into automating that. CI/CD is just one example of several. And then lastly, how do we actually verify mission success, and how do we do it easily? So is there a way to design our algorithms and to design our software where verification becomes easier? That's a big objective of ours. How do we actually, you can have all the bells and whistles, in the world, but how do we actually also make sure that the verification of those bells and whistles is successful? So yeah, we're doing a lot of awesome work. I'm so thankful to be a part of it. We've got some papers down here that reference both the algorithm that I talked about, energy management, as well as just a general kind of integrated analysis from a previous design cycle. We're planning on producing a lot more papers on integrated analysis in the future. We're really excited to kind of share some of the work that we've been doing. We're excited to kind of implement these new kind of agile methodologies into GNC development, and we're excited to kind of continue working with flight software and get something that is really slick, I guess you could say. Okay, so yeah, that's all I got. That's what you wrote. Again, this acknowledgement list, it deserves to be much bigger than it is. A lot of awesome people working on the MAV GNC team specifically, and a lot of good resources from guidance SMEs that have worked on shuttle, that have worked on SLS, that have helped us out a lot in kind of the initial ideation of energy management and how to get everything up and running, and good algorithm methodologies, what we should be looking into when we're designing this algorithm, so on and so forth. So lots of really awesome, talented individuals were able to help throughout this whole process, and yeah, definitely glad to be a part of it. So yeah, that's all I got, Neil.
Yeah, very, very cool, Jason. Thanks again for sharing that with us. Quite a tour de force there. A lot of material you covered. A lot of intriguing ideas. Let's see. Let's spend a few minutes going over some questions that we got. They kind of range the gamut. So the first, I think there was a little bit of confusion. You mentioned there was no avionics. That's on the second stage, right? So the question goes like this: if there are no avionics, how are the algorithms running and controlling the vehicle to achieve the desired orbit? Is something being controlled from Earth? Well, no, right?
Right. Yeah. So I apologize if I misspoke. Avionics are absolutely on the first stage. Second stage has a very simple time sequencer that we can just send time-based events from separation. So. And
the second stage is spin stabilized, right? Passive kind of.
That's correct. Yeah. Letting physics do the work for us.
Yep. The follow-up question was, are there any redundancies or backup plans if orbit isn't achieved?
Yeah, well, that's tough, unfortunately for
Yeah.
us. We have a very lean methodology, both to save mass and save development power. Yeah, lots of risk mitigation strategies are being used on, first stage to make sure we are on a ballistic arc to get into orbit properly. But yeah, unfortunately, if there's if there's no orbit, then unfortunately, we don't have a sample.
Right. Sad but true. The next question. During the burn stage, will it be active as you exit the atmosphere, or will the burn stage conclude prior to that and the rocket will coast out of the atmosphere?
Yeah, that's a good question. So the current vehicle design, now it changes every vehicle design, but the current vehicle design does have us still being in somewhat appreciable atmosphere by first stage cutoff. So by the time our first stage solid rocket motor is depleted, we are still seeing some significant aerodynamic forces on the vehicle. But that being said, it bleeds off very quickly after first stage burn off, and then most of the coast is outside of appreciable atmosphere.
Okay. Very good. Thank you. The next question's intriguing. It's more of an architectural consideration or question. What drove you to build all of the functionality, guidance, navigation, and control into a single CFS app? I think you called it the nav app, as opposed to making separate apps that communicate with each other over the CFS software bus. Does that make sense?
Yeah, absolutely. Good question. I'm gonna have to tell you to reach out to Stephanie Justice and Derek Biglari from the NASA flight software team. That was part of a design train that I was not part of. That being said, I could imagine that there are some interface simplicities with staying within one CFS app. And our code itself really isn't that large. Navigation is doing simple propagation. Guidance, the energy management is, somewhat longer, but other than that, very low code. So I feel like it'd be a lot of code development just for a very small app in the end. But that's a great question, a good architectural question. And
Yeah,
I'd be curious if they've considered that or not.
Yeah, we'd be interesting to know the trade there and what was considered. Yeah. Thank you, Jason. Let's see a couple more. Try not to wear you out. What is the FIDR fitter level that you have in GNC, because you have multiple IMUs and you have IMU fitter and so on?
Yeah, good question. A lot of the fitter development is still underway right now. We're still at very baseline in defining the IMU interface. A great resource is Michael Fritzinger, also part of our EV42 group. He's kind of like the nav SME for our group.
Okay.
But yeah, that's kind of his responsibility over the next few years to start developing up those fitter responses.
Nice, thank you. Let's see. Here's a question. Do you have a process or set of requirements for the Maverick plant/sensor models to be validated or verified against the Mantis models or actual hardware?
That is an excellent question. We actually just recently had a pretty productive meeting with JPL on defining their verification processes for individual models. So taking not a verification simulation, but verifying the models themselves. So actively something that the MAV team is looking into.
Mm-hmm. Critical stuff, right? Yeah. Okay, here's another question. When the second stage is targeting a specific target orbit, why doesn't it just target the highest orbit it can reach? For a sample return mission, wouldn't that reduce the delta V cost of the pickup vehicle, which comes and picks up the sample?
So it's a good question, but no, it actually doesn't. So the reason we're targeting a specific semi-major axis rather than the highest one, if you remember from orbital dynamics class, the rate that your orbit processes around because of J2 is dependent on your semi-major axis. The reason we're targeting a specific semi-major axis is because we are timing our orbital precession rate for the ERO to come in right at the same time, all the way from Earth, right? So we're planning that whenever our orbit precesses right to the right amount of time, that's when our ERO is going to rendezvous. If we were to just go to the highest semi-major axis possible, we'd get a different drift rate. And in fact, it would actually pretty drastically change the CONOPS requirement on ERO.
Okay. And maybe one last question. Let's see. Will the Mars lander of the future be designed to carry this Ascent vehicle to Mars? That's pretty open-ended question. Yeah.
Yeah, not sure. I guess TBD on that.
Right. Otherwise, I mean, people are saying great talk. Thank you very much. And I can only concur with that. That was a lot of material to cover. Very, very interesting. And thanks again for finding the time to share that with us. You've been very open. If people have subsequent questions or want to follow up on some of the key points you made, I guess they could reach out to you on email or give you a call on Teams. Is that okay, Jason?
Absolutely. Yeah.
Wonderful. Yeah. Okay, then let me try to get us off the stage then. Let's see if I can find what I want to do here. Bear with me. Yeah. So, yeah. Let's see. I just want to tell people the next GNC webcast will occur in May. We'll be announcing the speaker and the topic for that webcast in the near future. We are soliciting feedback on this particular webcast and also on the series of NESC GNC webcasts in general. Shortly, there'll be an email going out to all the registered audience participants, providing a link to our brief and simple online survey form so that we can collect your feedback. This email will provide the link where today's recorded webcast can be viewed online at the NESC Academy site. The webcast planning committee is always looking for ideas for future webcasts that would be of general interest to the GNC community practice. If you have ideas for other relevant GNC webcast topics, please contact me and share your thoughts there. If you want to arrange to give a talk, by all means, just give me a call. So thank you for participating with us today, and I hope you can join us again for the next webcast, GNC webcast in May. This completes today's NESC GNC webcast. So goodbye for now. Thank you.